So we will continue with properties of water and latent heat. Properties of water you're probably familiar with. As you learned in 7th grade, water has unique properties, and the most important of which in Earth system science is probably the fact that it is found within the range of Earth's temperatures, high and low, as a solid: ice, snow; liquid, the ocean and lakes and rivers and streams; and gas, the vapor that's in the atmosphere and is released from the interior of the Earth out of volcanoes. Now, you may have looked at phase changes of water during 7th grade, and phase changes are about how much heat has to be put into a system to melt ice or to boil water. And what people have discovered is that it's not the same amount of heat, and that's something that we could probably appreciate now that we understand specific heat of materials, and now that we know that the specific heat of water is so much more than the specific heat of ice. It's twice as much. So here's what's called a phase diagram, where we have on our y-axis the temperature in degrees centigrade from -25 to 125, and we have on these dotted lines gradations of heat being added in joules at a rate of 4 kilojoules. We don't know how much ice we're dealing with, but typically we would consider this to be 1 gram. So we'd have a gram of ice, and we'd want to know how much heat we need to add to it in order to change its phase from a solid to a liquid. And what we notice is that at a certain temperature below zero, say down to -25, we can add heat to the system. And you can see it's not going up very much, adding the heat, until we get to the melting point, 0 degrees. And at the melting point, suddenly the temperature stops going up, but the ice is actually now melting. This is where melting really takes place, at the melting point. And once all the ice is melted, boom, we keep adding heat and the temperature goes up. Now we have only liquid water, and we keep adding heat, but you can see the amount of heat has not changed that much, getting up to 100 degrees centigrade, where we have to pour in a considerably larger amount of heat in order to get all of that water to vaporize to a gas. 4, 8, 12, 16, whereas 4 times as much heat up here to get rid of that liquid and turn it into a gas. And then, of course, once it's vaporized, heat can be added, but the temperature won't go up. This is a phase diagram, and this is important in our study of the atmosphere and weather and climate, because the process of melting absorbs a certain amount of heat from the atmosphere, while the process of freezing releases some heat to the atmosphere. And even more importantly, the process of evaporation takes heat away from the surface of the Earth, while the process of condensation in the atmosphere releases heat when water changes from a gas back to a liquid or solid in the atmosphere as a cloud. And this change in the atmosphere in particular is the next part of our investigation of the simple properties. That is, when water is vaporized / evaporated into the atmosphere, it carries with it the heat that was used to cause that vaporization or evaporation. How much heat in joules? So let's say we have sunlight pouring down on some water. Water will be evaporating from the surface, say, of a lake or stream, or on your hand as sweat. And that absorption of heat by the water can cause the vaporization, the evaporation, but that heat is taken away, and in fact your skin will feel cooler. Or the better example for that, understanding that, is this notion that when you get a shot, say, maybe you'll get a vaccine soon in the next months, get that alcohol on your arm, it immediately feels cold because it vaporizes so quickly and takes the heat away from your body. Well, that heat, the area from which the water vaporized is cooled, doesn't raise the temperature in the air where it is now transferred to. There's no increase. That heat is just trapped within that water vapor, and it is known as latent or hidden heat. Latent or hidden heat. And that latent or hidden heat comes back into play as the water vapor rises into the atmosphere and gets to the point where it can condense, where it's low enough temperature that the water goes back into the liquid phase or the solid phase and releases all of that heat into the air or into a cloud. So that if you go up through the air, from the surface of the earth, through clear air, you have this one rate of temperature change, 1 degree per every 100 meters, or 10 degrees for every 1,000 meters. But if you go up through clouds that have a lot of water vapor in them, then there's heat in there, and the rate of temperature change is lower, from 6 to 9 degrees per 1,000 meters. And that lower temperature of the air column, that column of air, is caused by this release of heat. And this condensation, this release of heat via condensation, is critical in our understanding of thunderstorms, hurricanes, tornadoes, the weather in general. People are constantly monitoring what is called the stability or instability of the air and the temperature change going up in a column of air through air that has lots of water vapor in it and lots of condensation versus dry air. And knowing how that rate of change is different can help us forecast the weather. So latent heat, hidden heat, is a critical part of our understanding of water in the atmosphere and our weather. With that, we will just try to summarize by saying that air is cooled after vaporization. So air near the surface of a lake or a pond or the ocean that is very still, where vaporization is going on, evaporation, there will be a cooler temperature right near that surface than just slightly above it, or maybe even in the water just below it. Maybe not. But there's a cooling right at the surface. You often feel that if you play a sport on natural grass. Try this in the summer if you play a sport on natural grass. Lie down on the grass on a hot day and you'll feel it's cool. Put your arms out and just above the grass and you'll feel this cooler temperature because the plant is evaporating, evapotranspiring into the atmosphere, and that's lowering the temperature near the plant, the leaves of grass. Energy gained and lost by water when it changes phases. 4 major phase changes. Again, melting, freezing, vaporization, and condensation. Now, what are we getting at here? We're getting at numbers. How much actual heat? The heat energy gained during melting is 334 joules per gram. The heat energy released during freezing is 334 joules per gram. So melting and freezing are mirror images. One loses heat, one gains heat. We gain in melting, we lose in freezing. Then, up in the atmosphere and near the surface of water, we need 2,260 joules to vaporize or evapotranspirate the water to begin with. But then to recondense it, we need to lose 2,260 joules per gram. And this is, of course, critical in our understanding of the weather. Finally, the Earth Science Reference Table indicates to you that liquid water is actually denser. I knew I would get it wrong. And liquid water at 3.98 degrees, about 4 degrees centigrade, is actually denser than frozen water. Therefore, frozen water floats, which is kind of important in the evolution of life, because if lakes and ponds and oceans had all frozen solid, life would have had a lot more trouble continuing its path towards this moment in time. And this diagram of how much energy is gained and heated by these processes of melting, freezing, vaporization, and condensation can be found on the reference table. Finally, there's 2 more ways that water changes phases in the atmosphere. One is called sublimation, where ice changes directly from a solid to a gas, releasing 2,842 joules per gram. This happens in snowy areas of the world where the snow melts directly. It doesn't pass through the melting phase. It just goes directly from a solid to a gas. You also see this with dry ice. That's why dry ice can produce a cloud of fog in a theater, make it look like there's fog on the ground, because the carbon dioxide, dry ice, going from a solid to a gas has a density greater than the air, and it sits low on the ground and is used for atmospheric effect. Then there's deposition or desublimation, where water vapor changes from a gas directly to a solid, releasing, again, the same number of joules of heat per gram, this time releasing as opposed to in sublimation absorbing. And this is what known as frost or hoarfrost. And with that, we will stop in order to